Hey, welcome back to Comp 1113, Unit 5, video number 2. Today we're talking about Karnaugh maps. This is our method for optimizing Boolean expressions. So we'll construct optimal sum of products form and the optimal product of sums form. Let's get right to it. A Karnaugh map is basically just a truth table. We're going to rewrite our truth tables in a different way that will allow us to do some simplification directly from this modified truth table. We know that we can get canonical forms from a truth table, but we also know that those canonical forms are not necessarily the most optimal way of writing an expression. So our goal here is to write our expressions in simplified form. This will be useful certainly if you're programming and you're considering a complicated if statement. It will also be useful when we're designing logical circuits. We would like to make our circuits as simple as possible to minimize the amount of components that we'll need to construct them. So our goal in this rest of this unit is all about optimizing our Boolean expressions. So we'll start out with this new thing called the Karnaugh map. It's something we basically already know because it's just a truth table rearranged in a different way, as you'll see. Here's a truth table as we all are used to seeing it. Two input variables, x and y, and the function is s. I'm just going to rewrite this table in another way. Basically, we'll have our x variable on one axis and our y variable on another axis. And so we have a grid, and each spot represents one row of the truth table. So this first box here in the upper left quadrant is when x is 0 and y is 0. So basically this one in row 0 goes into this box. And then the next box over is x is 1, y is 0. Well, you can see that that's actually this row. So we should work down. The first one goes in this box. The second one goes in the box below it. The third one goes in this box. And then the last 0 goes in the fourth box. This is just rewriting the truth table. And it gets this fancy name, Karnaugh map. We have n input variables, so there'll be 2 to the n squares. I did the 2 variable case here, so 2 variables, 2 to the 2 is 4 squares. When you have 3 variables, the Karnaugh map has 8 squares, 4 variables, it has 16 squares. This Karnaugh map allows us to do simplification, believe it or not, because we can start to see what things might have in common. Like I can view this table and start looking at, say, these two ones and say, well, these two ones have something in common. They both start with y is 0. Or I could look at this group of two ones and say, well, these two ones maybe can be grouped because I know that they both start with x is 0. Basically, each individual term in the Karnaugh map is a min term. This is M0, M1, M2, and M3. I guess I shouldn't say that. If I'm only talking about min terms, I should just say the one. I should only look at the ones. So M0, M1, and M2. Each location is also a max term, but in that case, I'm only looking at the zeros, so I'd have an uppercase M3 here. But we can do better than that canonical form from this Karnaugh map. We can actually start to simplify. But just so we can get a feel for how we could maybe read one of these things, if I wanted to get the SOP canonical form from this, I would look at this. You remember, you look at the ones, and x is 0 there and y is 0 there. So we write that as x naught ANDed with y naught. And we can do that for all the terms. This is x naught ANDed with y, so we'll add that on. And then the final one is x is a 1, y is a 0, so x is positive and y is knotted. That's the SOP canonical for this expression. But we can actually do better than that, and we can start to simplify. If we look at what it takes to be in this group, now, again, we're talking about an SOP form. If I know that x is a 0, I'm in this group. It doesn't matter what y is. It doesn't matter what any other variable is. If x is 0, I'm in this group. And for x to be 0, I represent that with x naught. We can make another group, we mentioned it earlier, where we could group these two together. Oh, I'm proving it now. There, that was weird. The animation got a little bit off, but that's okay. When we look at this row here, it's a group of 2 ones. Even though it overlaps with one that we've already used before, that's okay. What does it take to be in this group? Well, y is a 0. If I know y is a 0, I know I get a 1. So to represent y as 0, I write y naught. Now I've represented the first group with x naught and the second group with y naught, and I'm done. And it turns out that using the theorems, we can get to that same expression, but we don't need the theorems anymore. We can basically go straight from the truth table to the optimal SOP form. We'll have to learn what the rules are for making these groups, obviously. It does seem weird that we, overlapped perhaps, or what are the rules in terms of why didn't we just do a group of 3? The reason we didn't do a group of all 3 ones is it would be impossible to write what all 3 have in common. If you have a group of 3, it's impossible that they all have one thing in common. So that's why we don't do groups of 3. So here they are, sort of the rules. Group adjacent squares, either side to side or up and down. And if we're doing SOP form, we'll be grouping 1s. If we're doing POS form, we'll just start grouping 0s instead. This is just talking about the number of squares that are in your Karnaugh map. It's related to the number of input variables you have. When you're doing that, you want to do them in powers of 2 for your groups. Powers of 2 will have things in common. So you can have groups of 1, groups of 2, groups of 4, groups of 8, groups of 16. But don't try to do odd numbered groups. They don't work. When you're doing this, you're looking for optimal form. And to get optimal form, that means you want big groups. So the biggest group you can get, the better. You're allowed to overlap. The only downside here is you can overlap to a point. You want to make sure that every time you make a group, it has something in it that's in no other group. And that's what this sentence is trying to get at. So you don't want to overgroup, because then you'll end up with a term that you don't need in the expression. Here's a 3-variable example. We'll put 2 variables along one axis and the third variable along the vertical axis. So I'll put my xy across the horizontal, and I'll put my z on the vertical for a 3-variable xyz Karnaugh map. And I'll just put my possibilities for x, y across the top here. So in this first spot, 0, 0, another possibility for x, y is 0, 1, and another possibility is 1, 1, and then 1, 0. And then all my possibilities for z are 0, 1. There is something weird about this table in that this spot seems out of order. Like, it's clear that this is the number 0, and this is the number 1. But then I jumped to the binary number 3, and then did the binary number 2. And there was a reason for that. When we're translating our truth table into this thing, we'll want to heed that. We'll want basically these two columns, this column and this column, are swapped around from their natural order in the truth table. And the reason for that is we want adjacent columns or adjacent rows to have things in common. Take a look at this. In the first two columns, I have x is 0 in both of them. So they have something in common. If I look at the second column and the third column, because I've rigged it so that the y value is a 1 in both of them. Had I put what I, sort of naturally expected to put here, had I put 1, 0, 1, 1 there, if I look at these two columns, they have nothing in common. Their x's are different and their y's are different. So that's the reason for doing the little swap, is that we want adjacent values to match. Now I have a 1 here and a 1 here. So these two columns have something in common. So we can make a group there. And by doing that swap, it still preserves the x's are both 1s in these two columns. And something really cool also happens when you look at the last column and you look at the first column, they also have something in common. The y is a 0. So you can basically have this column, you imagine that it's touching the other side. Basically, you're imagining that this thing is a cylinder. We've just written it in 2 dimensions. I tried to label this thing so it's basically what we just said. The first two columns have x is equal to 0, and in SOP form, that means x is not. And then the next two columns have something in common, y is equal to 1. And the last two columns, they have something in common, x is equal to 1. So we write that as x. So here's the middle columns, y is both 1 in those. And we even notice that the last column and the first column have something in common, y is equal to 0. So I could mark those with both y naughts. And then, of course, going on the vertical side here, well, there's nothing to group because it's one row is for 0 and one row is for 1. And 0 we would denote with z naught in SOP form, and we would denote it as z or 1 as z in SOP form. If we were looking at our POS version of this Karnaugh map, I would just change everything that's not wouldn't be a knot, and everything that isn't a knot, I would add a knot to, so that you can still view the table the same, well, just the opposite way. Here's an example. I have this little truth table here. I have x, y, and z as my inputs, and then my function is p. I don't know what p is yet, but here's its truth table. What we can do is take this truth table and populate our Karnaugh map with it. This first square here is x is 0, y is 0, z is 0, which is the first row. So this first one goes into this first square. Like that. And then the next one goes in the square below it. And then the third value there is a 0, it will go here. The next value is a 1. It will go here. Now, if things were working out properly, we would put our next value in this square. But think of it like this. We swapped these two columns around, so our next value is going to go in this square. Just check it out. X is 1, y is 0, z is 0. That's this square. X is 1, y is 0, z is 0. So this next one in my list goes in this square. So I was trying to show that there that I was skipping over that column to put our value here. And then the next one goes below it. So I'll put a 1 in the one below it. And now I can go back and fill these two in. So this next value is a 0, and it will go here. And then the last one finally goes here. It's weird that the last value of the table ends up kind of in the middle of the Karnaugh map. But now we have a Karnaugh map, and we could write the canonical form from this. Like we could have done it from the truth table, or we could just do it by looking at the individual ones from the Karnaugh map. Basically, you can just kind of come up with a pattern. You know, it goes 0, 1, 2, 3, and then it skips over 4, 5, 6, and then 7. Here is the canonical form. This first one here is x is 0, y is 0, z is 0. So I would write that as x naught, y naught, z naught. And then the value just below it is x is 0, y is 0, z is 1. And that's this term right here. So each one of these ones in the table is a term in this expression. So there are 6 ones in the table, so there are 6 products that get summed together to create a sum of products. But it's not optimal. This thing simplifies quite nicely. I said in the rules that we should look for large groups of ones. So I guess I have a table with 8 things, so I should try to find 8 ones altogether. Well, that's impossible. There are only 6. So now I'll start to look for groups. It's not multiples of 2, so I don't look for a group of 6. I'm looking for powers of 2. So I'm going to look for a group of 4. And, you know, this row of ones is kind of standing out there as a group. So let's circle that. And then ask, what does it take to be in that group? To be in this group of ones, z is equal to 1. It doesn't matter what x or y are. If I know z is 1, I'm in this group. So that's just z. Now we want to look for more groups. I could group this one with the one below it, because we're allowed to overlap, and make a group of 2. But better yet would be to take these 2 values and group them with the 2 values in the first column, because we said the first column and the last column have something in common. You can actually view them as touching. So rather than doing a group of 2 here and a group of 2 here, which I would then get 2 terms in my expression, it'll be better to make a group of 4, and I will only have 1 term in my expression. So I'll denote that. I'll make it look like it's wrapping around. So these 2 ones are touching these 2. And then I ask, what does this column have in common with the last column? And I look at their values. It goes 0, 0 here, and 1, 0 here. They both have y is equal to 0. If y is 0, it doesn't matter what x is. It doesn't matter what z is. If y is 0, I'm in this big group that's wrapping around. So y is 0 means why not? So this big ugly expression, in its canonical form, can be reduced to this nice, very simple sum of products form. It doesn't even look like it's a sum of products because it's so simple. Z doesn't really look like a product. Neither does Y not. So that's basically how you do these Karnaugh maps. We can do the same thing with the POS form. Instead of grouping ones, we would just group zeros. It's kind of neat if, in fact, in this case, the optimal SOP form will exactly equal the optimal POS form. It's not always the case that that's true just by where the ones and zeros fall. Sometimes the optimal SOP form will be a little more optimal than the optimal POS, just based on where the ones and zeros fall. If I were to circle the two zeros, I could ask, what do those two zeros have in common? Well, they have Y is equal to 1. They're both in this column and the next column. And I'm in a row where Z is equal to 0. So Y is a 1 and Z is a 0. And in POS, you do the opposite. So when Z is a 0, that means it's positive. Check that out. And when Y is a 1, that means it's negative, and you add the two things together. So it's the same whether we solve this as SOP or POS in this example. I tried to show you how it sort of wraps around so that this one is that one, and this one here is that one there. So you can kind of see how to visualize this. So there's the bottom row of that cylinder, and then the wrapping around ends up being projected on the sort of the back side of the cylinder. That's a few hours of my life I will never get back. Trying to get that to look right. We should go back and, enjoy that for one more second. 4 variables. I don't know why we often do this, but we do. I've noticed in a lot of textbooks, the order on the truth table goes X, Y, Z, and then the next variable is U. But it doesn't matter what the variables are. We could have A, B, C, D, but I'll point that out first. When you're making a 4 variable one, you'll notice that, the first pair looks normal. That's the number 0. Then you have the number 1. But look at that. We swapped again. These two columns you can picture as swapped around. And when you go down, you do the same thing. The number 0, the number 1, then the number 3, then the number 2. Again, and the reasoning is all about always keeping, the first 2 rows here have 0 in common. The second 2 rows have 1 in common. The third 2 rows have 1 in common for the X or the Z variable. And actually, the last row and the first row both have something in common as well. They have U is equal to 0. Same with when you're doing columns. The last column has something in common with the first column. So right now you should be trying to imagine what this thing looks like. It's not a cylinder. It's even worse. You end up with essentially, it's not a sphere either. It's a donut. Or if we want to be mathy about it, it's a torus. But if I were to label this thing, first 2 columns have something in common. It's a 0, and for X, so that means X is not. And the next 2 columns, they have something in common. That's X is 1. And then the middle 2 columns have something in common. They have Y is 1, and then Y is 0 in the first and last. And you can do the same thing with the rows. Here's where Z is 0. The last two rows are Z is 1. Middle two are when U is 1. And the top and bottom touch each other as U is 0. An example, I have my truth table with my 4 variables x, y, z, and u, and I have my function q. I don't know what its expression is yet, but we'll find out soon. I don't want to do the canonical form for it because there are so many ones. It's going to have 1, 2, 3, 4, 5, 6, 7, 8 terms, and each of the terms uses all 4 variables. Or I could do POS canonical, and it will also have 8 terms because there are 8 zeros. So let's see if we can simplify it. Let's not write the canonical necessarily. We can now start looking for optimal very fast. We just have to learn how to convert from this truth table to the new Karnaugh map. So again, the first spot or row 0 goes in the upper left corner. And then the next one goes just below it. But now you have to remember that we've swapped these two spots around. So this third 0 in the table isn't going to go in this box. It's actually going to go in the one below it. So skip over 1 and put the third 0. This 0 goes down here. And now the next 1 will go in the spot that we skipped. And then we go up to this spot for the next group of 4. So the next group of 4, we start with a 1, then there's another 1, then there's a third 1, which we'll skip. We'll go to here. So skip the third row there and write the third 1 here. And then the next value, I think, is a 0. Yeah, this 0 will go in the spot that we skipped. Now the tricky part again, we want to write the next one here, but we have to remember that these two columns are switched around, so we jump to this spot. So the next value in our list was this 0, and it goes up here. And now we're going to have another 0, which will go just below it, and another 0 that will go down here because we're skipping a row, and then come back to this spot, which is 1. And our last 4 go 1, 1, 1, 0. So we'll go 1, 1, and then skip a spot, 1, and then finally the last spot that we fill in is again kind of weirdly placed in the middle. Skip and fill in the spot. Now we've successfully translated from our regular truth table into, again, this is a Karnaugh map is a truth table. It's just in a different order. But the order allows us to do the grouping. So once we have this, we could, well, I mean, I bet I put the canonical form here just so you could see how ugly it was. This is basically to make the canonical form, basically circle it poorly. Do groups of size 1. So this 1 right here is x is 0, y is 0, z is 1, u is 1. This spot is x is 0, so x naught, y is 0, so y naught, then z is 1, u is 1. So this 4 variable term represents this single 1. But that's why we don't like to do small groups. We like big groups, because then we can cut down on the number of terms in the expression, because we'll have fewer groups in total. And the bigger the group is, the fewer variables it takes to represent it. I'd like to make a group of 16 ones if I could, but there aren't. So then I look for a group of 8 ones, and I don't see a group of 8. Next, look for a group of 4. I think we all see a group of 4 kind of staring at us right here in the middle. So let's circle that. Ask yourself, What does it take to be in this group? I don't personally ever write all these labels around the outside of my Karnaugh map. I just did that for teaching you how to do it, the first time. I basically just look at what, you know, what are the labels on the rows and columns. To be in this block, I can see up above it that the two columns both have y is equal to 1. And when it's a 1, that's positive, so I just write a y. And then what does it take to be in this group from the row standpoint? Well, they both have z is equal to 0, and I not my zeros. So I'm going to have y is 1, z is 0. So y is positive and then z is knotted. And now go and make another group. You can see there's a group of 2 1s here, but it's better to make a bigger group if you can. So let's take these two values and group them with the top two. They wrap around and touch each other. Oh, I did the wrong thing. I did it out of order. Okay, here's a group on the side. The best I can do with that group is a group of 2. What does this group of 2 have in common? Well, I can see that y is 0 in those two columns, right? This column y is 0 and this column y is 0. And then to be in this row, z is 1, u is 1. So we'll write x is 0, which will be x naught. Oh, sorry, y is equal to 0. So we'll write y naught. And then z and u are both 1s, so we'll leave those positive. See how a group of 4 only has 2 variables, and a group of 2 has 3 variables. So you can see why you want to have larger groups, because they have fewer variables. And now finally we can get to the one I was trying to do, which is these two touching the top 2. In that case, I have y equal to 1 in the columns, and then in the row, I have u is 0 in this row, and u is 0 in this row. So I'll write u naught for that. It's going to be y u naught. Now this is the optimal form of this expression. It kind of looks like maybe you could simplify it a little bit, and maybe you could make it look a little nicer with a little factoring, but it wouldn't be in an SOP form. This is the optimal SOP version of this. So there might be something that looks maybe a little simpler, like maybe I could factor the y's out of these two terms, or maybe I could factor something else. But I won't be able to cancel any of these terms out. There'll be no absorption or anything. So it's pretty slick. The amount of work to take this ugly canonical form to turn it into this, beautiful optimal form. I mean, that would be a lot of effort using the theorems. But we could do it, but it would take us a while. Let's contrast this with the POS version. In POS form, you translate your truth table to the Karnaugh map the exact same way. So for the expression that we had, we would put it in the exact same way we did. It's just that all these labels would now be reversed in POS form. So I'm just swapping everything around because that's how POS works. And now, instead of looking at the ones, we focus our attention on the zeros. So you might see a group of 2 zeros here, or a group of 2 zeros here, or maybe this one's all by itself. We want to make as big a group as we can. So look for 16 zeros first, you can't. Look for 8 zeros that are all touching each other, you can't. So now look for 4. And there is a group of 4, surprisingly. if you look at these two zeros, they actually touch these two zeros. And then you ask, what do they have in common? Y is 0 in the two columns, and then Z is 0 in the two rows. So Y is 0, Z is 0. In POS form, remember, zeros don't get knotted. So I'm going to write just Y and Z, and remember that we add them together in POS form. So this first group will be a term Y or Z. The Y is 0 in the columns, and the Z is 0 in the row. You can see that in the little labels here. I have Y as positive here and here, and I have Z being positive in these two rows. How about this group of 2, huh? A group of 2 will take 3 variables to represent it. In the columns, they both have Y is equal to 1. And when it's a 1, remember, you're going to make it Y naught. And your Z and U are both 1s if you're in this row. It doesn't matter what X is. If you know Y is 1, Z is 1, and U is 1, you know you're in this group. Which means I'm going to have to negate all of them because they're all 1s. Y is 1, Z is 1, U is 1, and I OR them all together. We're almost there. For our optimal POS, we have this 0 here. I could circle it by itself, and I'd have a group of, it would be a group that had 4 variables in it. But it'd be better if I could do a group of 2. You can't do diagonal grouping because if you go on the diagonal, you won't have enough in common. A group of 2 on a diagonal you can't represent that. But I can take this 0 and I could wrap it and have it touch the 0 that's above it. So I could make a group of 2 that way. Or better yet, I could take that 0 and have it touch the 1 over on the opposite column. So these two zeros are actually touching each other. Have a group that, I broke the, I thought I did 2 steps there in the animation. Okay, I broke the surprise to you. This 0 touches this 0, but this 0 is touching the 1 up here, and this 0 is touching the 1 over here, which is touching the 1 over here, which allows us to make a group of 4. So if you ever played bingo before, you'll know that 4 corners is a winner. And in this case, 4 corners are all touching. And you ask, what does it take to be in the 4 corners? Well, you'll notice that Y is 0 in the columns, and in the rows, you'll notice that U is 0. So Y is 0, U is 0. So it'll be Y plus U. You don't put knots when you're in POS form. So that's pretty neat. This is the optimal form in POS. And now remember, it's the same expression. Like this Boolean expression equals the one that's below. It's just that one is in the optimal SOP form and one is optimal POS form. Sometimes one looks easier than the other. In this case, it's about a draw. When you think about the number of operators, this one has 2 pluses, and there are a bunch of ands here. It's 2 pluses, and then 1, 2, 3, 4 ands. So 2 pluses, 4 ands, that's 6 operators, and then it has 3 knots. So 9 total operations. When we look at our POS form, we have a bunch of ORs. 1, 2, 3, 4 ORs. But then we have 2 ands. So 4 ORs, there's an and between the brackets. So there's 2 of those. And then the 3 knots. So these expressions have the same amount of, number of operators. So the number of things you'd have to actually determine. So they are, equal in a sense. I tried to draw that Karnaugh map in 3D so you can see that this corner touches this corner, touches this corner, touches this corner. Basically, think of it as a cylinder first. Have this column touch the last column, and then roll it so that the two ends touch. What do you do with 5 variables? That's the real question. It gets real nasty as you get more and more variables. One way to do it is to basically make 2 tables. So I have an ugly looking 5 variable expression. It is in SOP form. Product plus product plus product plus product plus product. But it's not the canonical form, and it's not the optimal form, I presume. But I can put this thing directly into a Karnaugh map. I don't even have to make the truth table first. But I have to get used to the whole idea of, oh boy, how do I make the 5th variable show up here? Well, I can have one table when E is 0, and I can use the other table when E is 1. And then I can try to translate these pieces into the table. And I can do it directly because it's in SOP form. So these terms will tell me where to put ones in the tables below. Example, ABC means A is 1, B is 1, C is 1. And then I go into the table, and everywhere in the table where A is 1, B is 1, and C is 1, I put a 1. So here's where A and B are both 1, this column. And now, where is C1? It's in this row and the last row. So these 2 spots. But I also have to do the same thing in the other table because I don't know, it doesn't matter what E is. I know that if A, B, and C are 1s, that a 1 goes in the table. And then we can do the same for the next term. This one is A is 1, B is 1, E is 0. So now I just have to look at this picture because I know that I only have to deal with E being 0. So I can forget about the one over here. So I just need to know when A is 1 and B is 1. Well, that's this spot, this spot, this spot, and this spot. Notice we can't have any contradictions. So if there's already a 1 there, we better be putting a 1 on top of it. And that's the case with this term. So this 3 variable term will be 4 1s. It's 1, 2, 3, and 4. So we overlapped a little bit, which is good news because that means it will probably simplify. With 4 variables, let's see where this spot ends up being. This is A is 1, C is 1, D is 1, E is 1. So I know I'm in this picture. I can forget about the picture on the left because I know that E has to be 1 for this 3rd term. And now I just have to put 1s in this table whenever A is 1, C is 1, and D is 1. So where is A1? It's in this column and the last column. And then I have to find where C and D are 1. So I'm in these 2 columns, and then I'm looking for C and D both being 1. So that's here and here. So these 2 spots. Hopefully you can see my cursor on the screen, or I'm really just blowing a lot of hot air for nothing. So this 1 showed up, and this 1 got overwritten, but it was already a 1, so it's still a 1. We can do the next term. B0, C0, E0. First thing I do is I look at the E. So E is 0, so I know I'm in this picture. I don't have to worry about the one on the right. I'm just looking at the one on the left. And now I want to know where B is 0 and C is 0. So where does that happen? Here's B is 0, C is 0. And here is B is 0, C is 0. And here, and over here. So we get these 4 ones just appeared. Last term, we have A is not, so A will be 0. C is 1, D is 1, E is 1. So forget about the first picture because that's E is 0. And let's go to the second picture where E is 1. Now we want A0, C1, D1. So A is 0 in the first 2 columns. And then we want to go to where C and D are 1. That's here and here. So that 4 variable term represents 2 ones. Everything else you just fill in with zeros. And now you just go on your merry way trying to make groups. You want to make groups of 16 ones if you can, or a group of 8 ones if you can. In this case, we can probably only make groups of 4. You probably see this column of ones here, maybe. That's what my eye was drawn to first. If you're in this column, A is 1, B is 1, and you know that you're in this table, so E is 0. A is 1, B is 1, E is 0. In fact, we already had that as one of the terms. Maybe you see another group of 4. Maybe you see this group here. But that would be, if you did do, this is a reason why you might want to group the whole thing before you start writing down the terms. Because if you group these 4, you'll find that you'll ultimately group this column with the other side, and you will have made a group you didn't need. Like you don't need a group of 4 that I'm circling right now, because all of those ones will get taken care of if I do the wraparound group here in magenta. And then what does it take to be in this weird group? Well, I see that B is 0 in those 2 columns, and C is 0. So that will be B naught, C naught. Don't forget that we're only in this table, so it's also in the E naught table. We've taken care of all the ones in this table. Let's go take a look at the other one. Certainly we see this row here. That's where C is 1 and D is 1, but we're also in the table where E is 1. So this group here will be C, D, E. And now we have this lonely looking 1 left. It could get grouped with the one above it and make a group of 2. And that'd be all right, but it wouldn't be optimal, believe it or not. It turns out that the tables are related to one another. You basically imagine that one of these tables is sitting on top of the other table. If you've ever played 3D tic-tac-toe, where you have 2 layers, or in tic-tac-toe you have 3 layers, and you can have the 2 layers essentially touching each other. So this group of 2 right here, I have 2 ones right in this spot. They actually line up with the 2 ones in this table. So they're touching. These 2 ones touch these 2 ones. And I ask, what does it take to be in that group then? You'll notice that they both have AB equal to 1. It doesn't matter what E is because it's in both tables. And then you just have to figure out what it takes for the rows. And in that case, C is 1. So we'll have A is 1, B is 1, and C is 1. And we don't care what E is, and we don't care what D is. So A, B, C. And that's the optimal grouping of this expression. These can get really hard. The one we just did here was actually very simple in terms of the number of, most of the groups stayed in their own table. You know, we had 2 groups in this table, 1 group in this table, and then 1 group that bridged between the 2. I tried to draw that in 3D. You know, basically we had our 2 Karnaugh maps, and that 1 group kind of reached between them to make a group of 4. When you hit 6 variables, I guess we add another plane. So we'd have 3 planes, you know, with any 2 touching each other, but the top layer can actually reach around and touch the bottom layer. Let's stick to 5 variables or less in this class. Usually there are some great computer algorithms that can solve these Karnaugh map problems. So once you get beyond 5 variables, you don't actually have to do this drawing. There are other ways to beat this problem. So hopefully you got a good overview of how to do some simplifying using Karnaugh maps. It's really kind of fun to do the grouping, but it is easy to make a mistake too. It's one of those things that you have to practice quite a bit so you stop making mistakes, especially when you get asked to do things like solve a question using SOP form, and then the next question says solve the question using POS form, and you have to kind of switch gears from thinking about everything being positive and ones to being more negative and zeros. But after you do practice that, you will be okay. I think you'll have fun with this. And soon we will do somewhat realistic or real world examples where this simplification, where we see the benefits of this simplification. But right now we'll focus on learning the technique of simplifying. So I think that's it for this one. I will see you all in the next one where we do some real world problems. Hope you all have a great day.